Alright, howdy class. Today we're going to finish off Handout 1. As you recall, we left off last time with an example with simple depreciation. Now we're going to continue on to talk about the cost, revenue, and profit. So first off, let's go ahead and define these terms. What is cost? Well, cost is what you're having to pay to make whatever product it is, whatever widget you're making, like that's got a cost that goes with it. And so we call this C of X, right? And so C of X, what is that? That's a cost function. That is a cost per unit manufactured. Now make sure that you're very familiar with this kind of nomenclature, right? Where you've got the C of X. Make darn sure you understand what that X means, right? I mean, that's what you're plugging in, right? The cost is a function of the number of units you are making. So cost per units manufactured. X stands for the number of units manufactured. All right, so the R of X, that is the revenue per unit sold.
I'm sorry, I think we're not going.
All right, my apologies. That was my daughter coming through. R of X, that is the revenue per unit sold. All right. So revenue per unit sold. So for the X stands for the number of units you sold, and so for simplification purposes, we'll just assume that in general that the number of units sold is the exact same that were made, though in real life this is not always the case. P of X, that is the profit per unit sold. Right, and so big difference here. Revenue, that's just the money coming in. The profit is the money coming in minus your expenses. So make sure you have those two differences firmly put in your mind. And we can write this as R of X minus C of X, right? The revenue minus the cost. So let's move on to fixed costs. Fixed costs are recurring costs that are constant, right? They don't change. So, for instance, rent is a good example. If you're having to rent the factory, right? That rent bill is coming through every month. Doesn't matter if you make 5 million units or if you make 0 units, you still have to pay rent. Variable costs are recurring costs that vary with how many units X were produced. And so, examples of varied costs would be, materials that go into make the unit, extra electricity used to run the factory. Although some people would argue that electricity is a fixed cost, but if you're using more electricity to make the units, well, then it becomes a variable cost. So it's kind of one of those, dicey ones as far as how you're defining terms, but. Let's get into some mathematical models now. We want to assume a linear function accurately models the cost function of a certain factory to produce X. So if you assume a linear model, it would have to take on this form, right? Because that's the form that all linear models take. And so notice here that the letter C, right, that is a variable cost. And notice that the letter F here, that is a fixed cost. And these are very much analogous. In fact, they are the same thing, right? The cost, for producing each unit, C, that's the same thing as our slope. And then notice that the fixed cost, that's the same thing as B. MX plus B all over, just different letters. So we are going to also assume a linear model for the revenue function. There is no just fixed revenue coming in, so we don't have to worry about a B, an intercept, and so it's just S times X, right? S is basically the sales price of your unit, multiplied by the number of units sold, S times X. Pretty self-explanatory. And so what is the profit function? So we have our P of X, and we defined up here that P of X is the same as R of X minus C of X, right? The revenue minus the cost. So assuming linear models for both, we have our little c times x minus, sorry, I put little c, the s times x, right, the sales price, right, your profit, your revenue coming in, minus c of x. And so here you've got the little c times x, right, the cost per unit to produce, times x plus your fixed costs right there. And so let me go ahead and highlight this to kind of show, right, that's our c of x there. And then here is our revenue function coming in, which we had right there. Alright, so go ahead and clean this up a little bit. So s times x, distribute this negative to both terms. And we're going to go ahead and group these two together so that you have s minus c, quantity, multiplied by x minus f. And so note for your profit, you know, how much money you make per unit sold, made and sold is given right here, right? And so note that is our M. And now our fixed cost right here, right? That's our going to be our y-intercept, and that is our b. Okay, so I had finished off this handout video, but the computer didn't save it, so I'm going to go ahead and re-record it. I already have the writing down, so we're going to go ahead and just scroll through it, and I'll explain everything that I have written as we go through it, rather than you watching me write what's going on for this one time. Alright, so we're moving on to supply and demand. We looked at fixed costs and variable costs before, and how do you calculate your revenue, how do you calculate your cost function, and then ultimately how you calculate your profit function. And we used simple linear models to model what we're looking at. And we're going to keep doing the same, more applications of straight lines. Do know that there are more sophisticated models out there to use, but right now we're just focusing on the straight line versions of those. Alright, so supply and demand. So the demand equation. What is the demand equation? It is basically a model that attempts to quantify how much how much a individual is willing to spend at a certain level of scarcity. And so that's important to note, that supply and demand, anytime you're looking at any kind of economic system, it's an attempt to manage scarcity. And so having said all that, it probably is important to identify exactly what we mean when we say scarcity. Scarcity, for our working definition, will basically be anything that you've got a finite amount of that not everyone can have as much as they want whenever they want. So let's think of a few examples. For instance, let's look at the example of air, right? Breathable air. Just not out in space, not down below the water, just right here in the coastal bend or anywhere where you find people walking around. Breathable air is not a scarce resource, right? You don't have to pay for breathable air. It's just abundantly available. There is more air than any of us could possibly consume. and we can all get as much air as we want. We don't have to pay a dime or a nickel for it. Note there is a finite amount of breathable air on this planet. It just so happens to exceed our ability to consume. That's a good thing. And so, for that reason, breathable air is not considered a scarce resource. So, we can identify what is a scarce resource as any resource that you have to exchange some kind of good or service for. Essentially, anything you have to pay for is a scarce resource, because if it were not a scarce resource, you wouldn't have to pay anything for it because it's just readily available, ready for you to grab. So anytime you have to exchange any kind of good or service, you are dealing with a scarce resource. So let's go ahead and do a quick thought exercise on this, then we'll go back to the demand function up here, but let's look over here right now. Quick thought exercise to help us understand scarcity a little bit better. Let's imagine you're driving along town, and you come down to the intersection. Could be any intersection. Let's say it's over there by Airline and Alameda. At that Exxon station sitting there, you see a Ferrari for sale with a sticker price of $5,000. This Ferrari is brand new. Nothing is wrong with it, and it looks so shiny and beautiful red. You might bring your car to a screeching halt, jump out of your vehicle to get to it to spend $5,000 on it. You might have to tackle over someone to get there first. Right, $5,000 would be a steal of a deal for such a fine automobile. Now, let's make an even sillier thought experiment. We're going to imagine we're on an alternate Earth, and on this alternate Earth, they have managed to produce so many of these fine automobiles, these Ferraris, that nothing wrong with them. And they're on every street corner. They're all over the place. You can't go a mile without seeing at least 3 of these Ferraris. And someone tries to sell that Ferrari for $5,000, well, they're going to be laughed right out of the store, wherever you happen to be, right? It's so commonplace, right? Everyone has quick access to it. So part of what gives the Ferraris their value, other than just being simply such a fine automobile, but the main thing that they get their value from is the fact that they are scarce. And so that goes back to our example of scarcity, right? Or concept of scarcity, right? Things have value because they are not readily available. So the demand equation is an attempt to quantify our demand for a scarce resource. So demand function, where we have P, and P stands for the unit price. And notice that this is a function of x. We will be using linear functions to model, but like I said, there are other functions, more sophisticated, but we're just sticking with linear for now. And our x variable here, x stands for the number of units sold, or number of units available, should we say. The fewer units that are available for sale, the higher the price will be, and then the more units available for sale, the higher, I'm sorry, I said that wrong. The more units available for sale, the less someone will be willing to spend for that particular good or service. So here we've got a simple demand curve, a linear model, as we talked about before, and we have this example right here. A small college town had 8,000 apartment units to rent to students. And so from this is basically read from the point of view of someone who owns or is a land developer. So the going rate at that time was $12,000 per month, right? There's 8,000 apartments to live in, and they have and they're willing to spend $12,000 a month for the right to live in one of these apartments. It's important to note that in this example it's a very self-contained, so it makes things a little bit more straightforward. If we had a whole lot of other variables moving in and out, we would have to take those into account. But this is a little more straightforward example. Some developers are building new apartments nearby, bringing the total number of units for rent up to 13,000 units, right? So 5,000 more units are available. And so they found to get 100% occupancy, the developers could only charge $10,000 per month. And I know in the handout initially says 1,000. I feel that 10,000 is probably more an accurate or emblematic number for this example. Again, I just kind of came up with numbers out of a hat for this one, so this isn't coming from any real data, but I'm trying to be as realistic as possible with this. So, assuming a linear model, find the demand equation. So, first thing we do, right, it's a linear model, so we want to find what the slope is. And one thing I would encourage you guys to do before even doing that is to just draw everything out like we have up here. So, when we have a mere 8,000 units, we're paying $12,000 per month, right? And that's our ordered pair right there. So at 8,000, I'm just going to write 8K, stand for 1,000, comma, they're paying 12,000. Right? That's our ordered pair. And then right here, we've got at 13K, that's 13,000. Well, then their students are only willing to pay 10K. Right? So definitely a drop per unit revenue, but if you have enough units, then you might not be losing money. So it all kind of depends. Now, if you're from the point of view of the person that had the 8,000 apartments, you're definitely not going to make as much money. Those new apartments going up are bad news for you. Alright, so slope, again, slope is always going to be rise over run. What the rise is and the run in will vary depending, or the meaning of that will vary depending on the example you're working with. Here, rise is the change in price that a student is willing to spend, and the run is the number of units available for sale. Alright, and so these triangles simply stand for delta. Delta is change in. Alright, and so we go from $12,000 to $10,000, and then 8,000 to up to 13,000 units. You run through the math, and you find that the slope is negative 40 cents per additional unit added. Right, so it's kind of important to kind of think through, if you just make one more unit available, is that going to be dropping the rent someone's willing to pay by 40 cents? Well, not precisely, but if you drop an additional 100 or so units, well, then they will average at about negative 40 cents per unit. And so that's just, when you're running through these models, you want to always be aware of their strengths and weaknesses. So we come over here and we set it up y equals, and we put in our slope right there. And then note that we're just leaving the y-intercept as an unknown constant. And then we substitute in one of our ordered pairs, one here and one here. And then we solve for b. And when we do that, we find that b equals $15,200 per unit. And so we put our model together, and this right here is the model that we were looking for, right? So here it's nice, you can just put in the number of units that are available, and then you'll see what your market is willing to bear. In this case, students willing to pay rent. Now, note that if you're in control of, say, the one with the original 8,000 units, you can drop the number of units available, and you will have a control over the price, that people are willing to spend. So if you just took 3,000 of your units off the market, well, then instead of there being 13,000 units available, then you would just put 10,000 units available. You plug the number in, you'd find P of 10,000, and that would be how much you could charge for rent and still get full occupancy. All right. So let's move on to the supply equation. The demand equation kind of models someone's willingness to spend. The supply equation models a manufacturer or producer's willingness to bring the good to market. And again, it's modeled very similarly. The supply equation has a P for unit price. It is a function also of the number of units sold. Okay. And again, the simplest supply curve is a linear model. Note that this one is increasing. And when you think about this for a moment, it should make perfect sense. The higher the price that you can make for a good, well, the more you're willing to make of that good. A good example of this is oil and gas exploration. As the price of a barrel of oil goes up, the more the willingness of companies to go out and drill more wells. And one thing that is sure as day, if that price drops below a certain number, you will see the number of rigs going out to drill new wells drop down precipitously. And that all has to do with the producers of oil and gas, or the exploration of oil and gas, their willingness to go out and bring that good to market. So we have another example here. In this one, before we didn't have quite as much legwork done for us. In this one we do. We already have a model someone has created for us. And so here, and this is a model for supply. We want to know how many units should be marketed if the apartments complex wants to rent their units at $1,300 per month. It's very similar to the previous example, but it is important to note that they're not necessarily the same. So right here we just restate the problem, and note that on this step here we solved it for P. That way we get in a nice slope-intercept form. And then this next step, we have simply set the price equal to $13,000 per unit, because that's what we want to sell our units for. Or should I say, that's the profit we're willing to accept. And so we set this up and we solve for our X variable here. And so in order for the manufacturer to be willing to produce, what we found was 31,200 units, they would need to be selling at a price of $13,000 per unit. Okay, so let's talk a little bit about mathematical models, how they're developed, and how they are refined. So you start here with a real-world problem. So it's important to note, what is a real-world problem? And so we're going to define a real-world problem in this class as an occurrence that has tangible data that needs to be optimized for maximum benefit, right? It's a business setting, so we want to maximize profits, of course. Occurrence, I'm trying to just keep more in just a common vernacular. In mathematical parlance, you would use the word variable instead of occurrence. And so we're trying to maximize our benefit by controlling the occurrences or variables that we do have control over. So after we've stated what our problem is, we need to begin to formulate. And so formulate basically is we're describing the data using mathematical equations, right? Usually in terms of one occurrence or how one occurrence affects the other. And so once we've formulated, we have our mathematical model. And what is a mathematical model? But it is a model that describes the tangible data through equations. And so this relates one occurrence to another via the equations that we have developed. And so once we have equations, we can find a mathematical solution. So we will begin solving those equations. So we're using the equations to find a mathematical solution. You know, the traditional solve for x statement. So what is a solution to mathematical model? It is the amount of independent occurrences. And so in this, when we say independent, it's the same as when we're talking about independent variable versus the dependent variable. That gives the optimal amount of the desired dependent occurrence. So basically, the independent occurrence is the occurrence we have control over, right? From the other example we're looking at, that would be we would have a certain amount of control over how many units are placed in the market, apartment units. And so for a particular desired outcome would be at what rent would we want it to go for. Now the next thing is interpret. What does the mathematical solution mean? So mathematical solutions are great. You know, you're trying to find the best solution, but if you don't think through what the mathematical solution means, you might have an actual terrible result. There is an old joke about accounting where an accountant will look at the books and discover the best way to maximize profits is to eliminate the payroll expense. So that basically would mean firing all your employees so that you have less expenses. Now, as we all know, this will not lead to a successful business, right? You've got to have good people working for you if you're going to do well. So always think about the mathematical solution and what the real world consequences of that solution will be. If the real world consequence is unacceptable, then you should not go with that particular solution. Again, always be aware of the limitations and strengths of your mathematical model. So once you have the solution of your real world problem, what is the solution of a real world problem? It is an interpretation of a mathematical solution into tangible objects or concepts. And so we've got one last step, right? Note that this is goes in a circle. You want to check the accuracy of your model in predicting known results, right? Basically, you just look at old data and see if your model can accurately predict things that have already happened. And as new things happen, you want to check your model to make sure it is still working effectively. Always be testing a mathematical model you've come up with so that you may refine it, right? You always want to be tweaking it to make it work better. And so most people do neglect this step. They neglect to test and refine the model. All right. So that is it for this handout. If you have any questions, feel free to email me. Do not forget to do the homework that is on WebAssign. Until next time, I hope you all have a great day and a wonderful week if I don't hear from you before then.